Let's say we observe some object. Let's say for the sake of argument, it's happening in space, and it's traveling in a circular path with the magnitude of its velocity being constant. And I want to be very clear here because the magnitude, so let me draw its velocity vector. So that is the length of this arrow is the magnitude of its velocity. But I want to be clear, in order for it to be traveling in a circular path, the direction of its velocity needs to be changing. So at this time, the velocity vector might look like that. After a few seconds, the velocity vector, let me do that in a different color so we can keep track of things. After a few seconds, the velocity vector might look like this. After another few seconds, the velocity vector might look like this. I'm just sampling from, I obviously could have sampled after less time and it would have been right over there, but I'm just sampling sometimes as it travels around this circle. After a few more seconds, the velocity vector might look something like that. And what I want to do is think about what needs to happen. What kind of force would have to act, and in particular, the direction of the force that would have to act on this object in order for its velocity vector to change like this. And let's remind ourselves, if there was no force acting on this body, and this comes straight from Newton's first law of motion, then the velocity would not change. Neither the magnitude nor the direction of the velocity would change. So if there were no force acting on this object, it would just continue going on in the direction it was going. It wouldn't curve. It wouldn't turn. The direction of its velocity wasn't changing. So let's think about what the direction of that force would have to be. And to do that, I'm going to copy and paste these velocity vectors, and then we can keep track of what the change in velocity, or especially the direction of the change in velocity, has to be. So let's say copy, and let me paste that. So that is our first velocity vector. Let me scroll a little bit to the right. So that's our first velocity vector. Let me copy all of these. This is our second one right over here. This is our second one. Let me copy and paste it. So I'm just looking at it from the object's point of view. How does the velocity vector change from each of these points in time to the next? And then let me get all of these in there. So then let me get this green one. Looks like that. So let me copy and let me paste it. Go put it like that. And then let me do, and I could keep going. I could keep drawing velocity vectors around this circle, but let me do this orange one right over here. So copy and then paste. So do just like that. So between this purple time and this, let me do it in white. Between this purple time right over here and this, and I guess this magenta time and this purple time, what was the change in velocity? Well, we can look at that purely from these vectors right here. The change in velocity between those two times was that right over there. That is our change in velocity. So if we were to take this vector, this little white vector that I did, and said, okay, in what direction was the velocity changing when the object was going on this part of the arc? Well, it was roughly, if I were to just translate that vector right over here, it's roughly going in that direction. So that is the direction of our change in velocity. This triangle is delta. Delta is for change. Now let's think about the next little time period. Between this blue or purple period and this green period, our change in velocity would look like that. Change in velocity. So while it's traveling along this part of the arc, roughly it's the change in velocity. If we draw the vector starting at the object, it would look something like this. I'm just translating. Actually, let me do it a little bit. It looks something like this. I'm just translating this vector to right over here. And then I'll just do it one more time. And let me do it in this blue color. So from this green point in time to this orange point in time, and obviously we're just sampling points. It's continuously moving. And the change in velocity is actually continuously changing. But hopefully you're going to see a pattern here. So between those 2 points in time, this right here is our change in velocity. And so if I were to translate that vector right over there, it would look something like that. Change in velocity. So what do you see? And if I were to keep drawing more of these change in velocity vectors, you would see at this point the change in velocity would have to be going generally in that direction. If at this point the change in velocity would be having to go generally in that direction. So what do you see? What's the pattern? For any point along this circular curve, what's the pattern? Well, the change in velocity is, first of all, it is perpendicular to the direction of the velocity itself. And we haven't proved it, but it at least looks like it. It looks like this is perpendicular. And even more interesting, it looks like it's seeking the center. The change in velocity is constantly going in the direction of the center of our circle. The center of our circle. And we know from Newton's first law that if the velocity is changing, and the magnitude could stay the same, but if the velocity is changing in any way, either the magnitude or the direction, or both, there must be a net force acting on the object. And the net force is acting in the direction of the acceleration, which is causing the change in velocity. So the force must be acting in the same direction as this change in velocity. So in order to make this object go in this circular path, there must be some force causing, kind of pulling the object towards the center, and a force that is perpendicular to its direction of motion. And this force is called the centripetal force. Centripetal. Not to be confused with centrifugal force. Very different. Centripetal force, centra, you might recognize, that means the center. And then petal comes from, it's seeking the center. So let me write that. It is center seeking. And so this centripetal force, something is pulling on this object towards the center that causes it to go in this circular motion. And that inward pulling causes inward acceleration. So that's centripetal force, a centripetal force causing centripetal acceleration, which causes the object to go towards the center. The whole point why I did this is that, at least it wasn't intuitive to me, that if you have this object going in a circle, that the change in velocity, the acceleration, the force acting on this object would actually have to be center, or it would have to be towards the center. And the whole reason why I drew these vectors and then translated them over here and then drew these change in velocity vectors is to show you that the change in velocity is actually towards the center of this body. Now, or towards the center of this circle. Now, with that out of the way, you might say, well, where does this happen in everyday life, or actually, I guess, in reality in some way, shape, or form? And the most typical example of this, and this is something that I think most of us have done when we were a kid, is if you had a yo-yo. If you have a yo-yo, let me draw my best attempt to draw a yo-yo. If you have a yo-yo, and if you whip it around on a string, you know that the yo-yo goes in a circular. It goes in a circle. It goes in a circle. Even though its speed might be constant, or another way of thinking about speed, the magnitude of its velocity might be constant, we know that the direction of its velocity is constantly changing. It's going in a circle. And what's causing it to go in a circle is your hand right over here pulling on this string and providing tension into that string. So there's a force. The centripetal force in this yo-yo example is the tension in the string that's constantly pulling on the yo-yo towards the center. And that's why that yo-yo goes in a circle. Another example that you are probably somewhat familiar with, or at least have heard about, is if you have something in orbit around a planet. So let's say that this is Earth right here. This is Earth right here, and you have some type of a satellite. Let me draw a satellite. You have some type of a satellite that is in orbit around Earth. That satellite has some velocity at any given moment in time, but what's keeping it from not flying out into space and keeping it going in a circle is the force of gravity. So in the example of a satellite, or actually anything in orbit, even the moon in orbit around the Earth, the thing that's keeping it in orbit, as opposed to flying out into space, is the centripetal force of Earth's gravity. Now another example, and this is probably the most everyday example because we do it all the time. If you imagine a car traveling around a racetrack, so let me draw a racetrack right out around here. If I have a racetrack, and before I tell you the answer, I'll have you think about it. So let me draw my best attempt at a racetrack. Actually, let me just draw a circular. I'm not going to even bank the racetrack. So let's look at the racetrack from above. So if I have a car on a racetrack, I want you to, and pause this before I tell it to you, because I think it's an interesting thing to think about, because it seems like a very obvious thing that's happening. We've all experienced, we've all taken turns in cars. So that we're looking at the top of a car. That's its tires. We're looking at the top of a car. And when you see a car going at a constant speed, so on the speedometer, it might just say whatever, 60 miles an hour or 40 miles an hour, whatever the constant speed. But it's traveling in a circle. It's traveling in a circle. So what is the centripetal force in that example? There's no obvious string being pulled on the car towards the center. There's no some magical gravity pulling it towards the center of the circle. There's obviously gravity pulling it down towards the ground, but nothing pulling it to the side like this. So what's causing this car to go in the circle as opposed to going straight? And I encourage you to pause it right now before I tell you the answer. So assuming you've now unpaused it, I will now tell you the answer. The thing that's keeping it going in the circle is actually the force of friction. It's actually the force between that resists movement to the side between the tires and the road. And a good example of that is if you were to remove the friction of the road, if you were to make the car drive on oil or on ice, or if you were to shave the treads of the tire, or if it was some type of a plastic tire or something, then a car would not be able to do this. So it's actually the force of friction in this example. So I encourage you to think about that.